Very good. Okay. So I have about 15 minutes to talk about 5 years of research, 4 to 5 years of research, and a vision for the next 5 years. Finger crossed if we have good news next week. For those who don't know me, I'm a summer institute kid. That's where I start to learn about FAME. My screen is not moving here. That's, oh man. Okay, we'll deal with it. That was not... Very quickly, so I started to learn about FAME about 4 years ago at the Summer Institute, and we worked on a project called Quick FAME. I can't take the credit for the acronyms, but the science was mainly done by Mark and Ankit at that time in our team. And Mark took it away, and he continued during his PhD. He developed something called CFAME, that stands for Coastal FAME, and Urban FAME. Both they were based on hand. He's in a lab at UT Austin where the mind behind hand FAME lives, Dr. David Maidman. One of the other amazing things that happened during that summer, we got the chance to hear from great scientists with great vision, Dr. Tom Graziano. He told us a lot of stories during that summer, the start of the QPF program at the Weather Service, the start of COMET with NCAR, UCAR, the start of the Summer Institute at OWP with Dr. David Maidman. But one of the things that still resonate, and it's relevant to this talk, he told us how the vision in OWP and in NOAA, it's grounded in the need of the end users, name it bunch of end users for the FAME products, including FEMA, and eventually he gave us the keys for Flat Fight. I know that few people here, they were there during the capstone. So I'll quote Tom directly. So he said that the top 3 things that we need are, any guesses what's the first thing? Good one. Second? Another right answer. Third? Very good. FAME. But when Tom mentioned FAME 3 times, that's not a random number, because it's a puzzle that we live in 3 different pieces. That's part of it goes to the hydrologic modeling, and I'll pretend for a second.
Oh, you're good. So is it working?
Yes.
Okay, great.
Yeah, I would. Yeah, part of it's attributed, or a part of the puzzle is the hydrologic modeling, and we'll try to pretend that the QP and QPF uncertainty comes in the same package with the hydrologic modeling. Another piece related to river and coastal hydraulics, and then the last piece when it comes to risk communication. Now, given the timeline, so the Summer Institute ended in July 2022, Cairo was awarded in April 2022, so within that same year, the projects within Cairo, they started. And basically what we did, so this work was basically done during the FAME working group, and one of the things that we worked on is reviewing the funded project, but honestly, the contribution and the efforts within the consortium, they are not limited to the project. There is more of a broad perspective of bringing science to action. FAME. Then, well, the first piece, the hydrological modeling. Second was the river and coastal hydraulics communication. You missed those anyway. So, back to the past, I would say 4 years to be fair to PIs and students working on those projects. It's mostly of a vision that brought science to action, and it was basically grounded in 4 main pillars. That's science with more than 50 publications, peer-reviewed publication, and one of the things that really stands here that most of the publications, they come with fair science perspective, with frameworks shared, reproducible frameworks and workflows to replicate the results that were presented and the advances presented in those scientific papers. The second is pillar is service, and here I'm highlighting one example from the Iowa Flood Center because I work there. And this is the integration of the Iowa Flood Center community flood maps within the partner FIM paradigm within the National Weather Service FIM services. So we have the partner CAT and then the dynamic FIM. So those maps now, they are part of the National Weather Prediction services. The other thing that it's integrated in the same service is the Iowa Flood Center bridge sensors. If I can, yeah, it's a small map here. So we have more than 300 bridge sensors there. They provide situational awareness when the river starts to raise, and several sensors now, they are integrated in the same service run by the National Weather Service. The other pillar is engagement, and that's valid from K-12 activities to engagement with national partners. Here I'm highlighting example from project led by Dr. Beverly Weppel, and here basically the initiative is targeting floodplain managers, also bringing new partners to Cairo like American Rivers and the American Flood Coalition. The fourth pillar is impact, and if we look at the past three R2O awards that they were granted within the consortium, so 2 awards, they went to FIM project. One project was related to river ice mapping and ice-induced hazards, and the second project that basically did everything. Now, that said, if we look at the portfolio, we have 4 main trust areas with confidence. I can say that we have expertise to tackle several problems within those trust areas, so spans hydrography to hydraulic modeling, intelligent and probabilistic FIM, and then operational integration and risk communication. If I would start with the first area, I'll try to be a little bit quick here because we have too many projects, but the mentality basically was very straightforward. It's operational oriented, and the target was to leverage institute data sets and data-driven methods to advance some of the operational capabilities within the weather service, such as here, and more specifically, HandFIM, and to provide a better representation and better estimation of some of the parameters that they are used for. HandFIM, one thing that stands out here, and I need to mention, is the FIMServe framework or service that is provided within this project. Basically, what you can do, you can come up with your own configuration, with your own data. You have the operational FIM mirrored in Cairo bucket, so you have the latest and the greatest product from the operational side. You can get it, change the configuration, run your own model, compare, and see if you are doing better. The other point that I want to highlight here, which is the integration of remote sensing data to update some of the HandFIM parameters. And this is really one step that would lead us to talk about dynamic representation of FIM parameters and dynamic hydrography. Other projects, they went beyond the banks and they looked at the floodplains, and here this is a project from the University of Vermont, or led by the University of Vermont, and basically what they try to do is to look at different characteristics of floodplains and channel geomorphology and the impact of that on the channel routing, basically by replacing the hypothetical representation of the channel by realistic channel, and then coming up with a classification algorithm to see where this representation is needed and where it's fine to use the simplified representation of the channel. It has direct impact on targeting regions where more data collection is needed. Now, if we move to the second trust area, so basically we had a couple of projects targeting process-based modeling, and those are type of projects that they were in close collaboration with operational partners. This is a project in collaboration with the Northeast RFC, where the team started by developing an automated satellite-based river ice monitoring system, and then used those information that they get from the satellites to feed it to 2D HACRAS model. This was originally developed by Environmental Canada back 2015 or 16, and then Northeast RFC continued the model to cover the entire Saint John River that's on the borders between New Brunswick and Northeast US. Again, this project also it has some direct impact to inform operational FIM development within the RFCs. Another project that also targeting physics-based modeling, and this comes from BYU and other partners, where they developed a platform where you can run hand FIM at the same time, and also at the same time you can bring maps from high fidelity models, and that's where we can really compare and get an idea which model works best where. Another project that, since we are going to the AI age, so the main thing that we need is big and large training data sets. So the model here, they run several simulations with Sphinx, and the contribution or the key achievement is not really to run models, is to create unique data set of compound flooding and validating that with remote sensing observations. Moving to the last trust area, which is third one, intelligent and probabilistic flood inundation mapping. You saw those images yesterday during the poster session, and also in the lightning talk. So basically, there are projects that they understood we really need probabilistic representation of the channel morphology, and the backbone there is basically the synthetic rating curve. So targeting the estimation of different parameters of rating curves and providing an uncertainty-aware FIM product that they tested at different scales. Another project or another key achievement was to prove or provide a proof of concept on combining the output of hand FIM with surrogate model to enhance the performance of the operational product. So this started at the Summer Institute, and this was a couple of years ago, before the surge of ML and AI models came to the FIM world. So it provided a proof of concept, and now there are a lot of developments that builds on such approaches. The last trust area, so it's more into the risk communication and decision support, and there are several projects that targeted the segmentation of audience and testing if those FIM products they could be digested by different audiences, including expert and non-expert users. So specific and well-established frameworks were conducted to improve the visualization of the product, and this was with the close collaboration with the Office of Water Prediction. Another project that targeted, or it was framed under the umbrella of user-centered FIM, FlatSavvy by Kwasi and Northeastern University. So basically, they targeted resilience practitioners, and they looked at retrospective simulations of stream flow, hydrographs, at the same time getting the flood maps. So the flood plain managers and the emergency managers, they start to develop the awareness, knowing how much stream flow would result in which inundation, and get familiar with the national water model and the output of the national water model in their day-to-day practices. Now, try to be fast for the next 5 years. Basically, the vision needs to be grounded in a map, since we are talking about flash inundation mapping. Most of us may think about the US as 50 states, but in the FIM world, we need to think about it as 13 river forecast center and 125 WFOs, because our first end user, those are the forecasters in the ground. The R2 pipeline, and at least how the working group is envisioning it, is to start with the FIM think tank, where we need to work closely with the operational partners and co-design and co-develop the, people they may call it the white papers, but the products, really understand what the forecasters they need at the WFOs level and at the river forecast levels. And then when the developing starts, then we move to the test bed phase, and there are, to achieve successful test bed, there are basically two ways. The first way is the right way. That's how I call this the NOAA way, and that needs to happen with a push from operational partner. We don't have a FIM test bed within NOAA. There is the hydromet test bed, the space weather test bed, but we don't have a FIM test bed. So the alternative is to do it in an academic environment, and that could be done basically within near real-time systems that provide output, and the forecasters then they can take a look at it. Then, if it's a successful test bed, you package and you give the weather service. The R2X, I will summarize, it should go to research to application, research to service, and touch the academic community and all different communities, and should happen with close coordination also with federal and regional partners. So our working group basically have 4 objectives. Our first objective is basically thinking about what happened during the past 5 years and thinking for the next 5 years. And the first question that we ask, do we need more data or more models? I think we are swimming in models, swimming in data. And what we envision is to have a Cairo-led flood compendium where we can put all the data in the same database, and basically making the life of modelers easier, so he can pick specific type of event. If you are modeling fluvial, you only go to fluvial event, so you have a data set that provide impacts, sources or data that comes from Cairo project, come from other sources, and it would make one step towards impact-based forecasting. What about models? Also, they need to be grounded in maps. We know that we have different needs across the different RFCs. Some they need to deal with coastal flooding, tropical flood, flash flood, floods. This is just an overview of the last 4 years of convective systems over the US, tropical cyclones, atmospheric rivers. Every region needs its own need, and we cannot have one model for everywhere. Going north, ice jams, 7 RFCs out of the 12, they suffer from ice jams. Derek already mentioned this, the main problem that humans, they just go directly to flood water. This is from 2008. This is 2008 study, 50% of, or 63% of casualties, they are vehicle related, and this is 2 weeks ago. So I don't think that the problem is solved yet. There are some good examples within NOAA that we could follow, similar to the impact-based decision support, and the way that we envision that is to bring to the table the likelihood with the impact in the same table, but more with fusion of prognostic and diagnostic model in the same framework. Similar to what Derek said, you can have the 5 days flood outlook from the RFCs or the dynamic hand frame. That's just one time step. It gives you an idea what could happen, and then you need high fidelity models to get to the street level. And we see as a cellular automate as an opportunity to develop high fidelity to D models. Probably we want to get to this level. People, when they see traffic, they avoid it. So maybe when they see red in some streets, they would avoid it. The $1 million question, what's the limit of predictability? How far are we from the limits? Probably the first one, we have some answers. How far are we from the limits of predictability? I think we don't have answers yet, except for Vitek Krajewski, if you know him. He said that forecasters need a time machine. You know it. In our world, it's called digital twin. So basically, probably that's what we need to provide forecasters with the necessary tool where they can test scenarios. If the rainfall or the QPF changes, if he have hydrophobic soil that he needs to deal with, if there is burn scars that he need to deal with. So giving the capability to forecasters to mimic Mother Earth. Can I finish with? Okay. So I will finish with Tom's words. He said the dam looks pretty doggone bright as we collectively advance this collectively. Thank you.